Hello, Heritage Academy Levine Scholars. This is Mr. Plum. I'm going to be teaching you science this year, and the basis of most of what we'll be learning this year is all about the scientific method. And I know you just had a pre-test on it, and hopefully this lesson I'm going to give you right now will clear up some of the confusion and answer some of the questions that you had. The pretest was to see what you remembered. So let's just jump right into this. The scientific method, as shown here, has 6 steps to it. And we're going to talk a little bit more in depth about each one of these steps and go through this and how each one works. First of all, step 1, the purpose. The purpose, another way to say that is to state the purpose or the problem or the question. What is it you're trying to discover? What do you want to know? Now, you see here this gentleman, his name Galileo Galilei. You see when he was born, and he was an Italian mathematician, physicist, philosopher, and astronomer. He gets credit for being one of the major contributors to come up with the idea of the scientific method. It's not correct to say that he invented the scientific method, because the scientific method is a way of thinking. It's not an actual device or piece of software. It's a way of thinking. So it's more of a philosophy, and he, along with another gentleman named Francis Bacon, are the ones who primarily came up with it. We aren't going to discuss Francis Bacon very much in here because we're going to focus on Galileo. He had more to do with physics and with what we are going to be learning this year. Step 2, research. Is your question clear enough? Find out as much as you can about the topic. What other discoveries are there like this one? Has anyone asked this question before or tried to disprove this idea? And so look at that picture that you see there. This was also in your pretest. This is a diagram from the Portuguese cosmographer and cartographer Bartolomeu Velho. And he did that in 1568. And this was the prevailing theory of the time of what our solar system and what our universe looked like. And the idea was, this is also known as the geocentric theory. The geocentric theory basically said that the Earth was the center of the known universe, and that everything orbited around the Earth. In that diagram there's orbits for Mercury, Venus, Earth, Mars, Jupiter, Saturn, and then beyond that was known as the firmament of the stars. We had not yet, at that time in 1568, they had not discovered Uranus, Neptune, or Pluto, or anything beyond that. That was the extent of their knowledge at the time. And so Galileo came up with his question based upon this prevailing theory of the geocentric theory. He looked at this model that this gentleman, Bartolomeu Velho, and others had put forward, and he looked at it and thought, okay. And if you think about it, it really not, I mean, we look back today and we think, wow, how could they think the Earth was the center of the universe? What was wrong with these guys? Well, in their time, you have to remember, no internet, no airplanes, no spaceships. They maybe had some balloons that could go up sort of high, but they didn't have satellites, and there was no Hubble Space Telescope, no International Space Station. They didn't have all the stuff we have today to give them more information. Science is based upon the information that you have at hand. So when you do your research, your research is limited to what is known. How can you do research on stuff that that hasn't even been discovered yet? So this was true in his time. So Galileo, though, was a very smart man. And a couple other things before I leave this slide: just make sure you have multiple sources and for your research, and that you use reputable sources. There's some stuff on the internet, as you know, that is not accurate. So just you remember Abraham Lincoln said that everything on the internet is true. Of course, I'm being sarcastic. There was no internet during Abraham Lincoln's time. So, but when you do your reports, you need to make sure you cite all your sources. So here's the theory that existed at that time, that the Earth was the center and everything revolved around it. And that picture on the top is the basic diagram. The one below, this is another prevailing drawing that was existed in that time. So Galileo, he made observations and he looked at the stars and the sun and the moon and how the planets that they had at the time, Mercury, Venus, Saturn, Jupiter, Mars, he watched them move across the night sky and carefully observed them, and he noticed some discrepancies, some things that didn't fit with the theory of the time. Mainly, he noticed that Venus and Mercury would never go very high in the sky. So if you guys have ever watched the stars at nighttime, you can see Saturn, you can see Mars, Jupiter, Saturn, and if you could see them with your eyes, telescopes, you can use to see Neptune and Uranus and Pluto, if you could see them. But you'd notice that they all move clear across the sky. There's an arc, and it's called the ecliptic plane that they all orbit on, except for Pluto. But you can notice that all of them move clear across the sky, except for Venus and Mercury. Venus and Mercury would only rise up so high in the sky, come down. So high in the sky and come down. And then the other part of the year, they would be on the western horizon, so high in the sky and come down. But Venus and Mercury never went clear across the night sky in a big arc all the way across. So this was a discrepancy that didn't make sense. It didn't fit with the theory. And this was one of the things that caused Galileo to question the geocentric theory. Now, his experiments that he did, it took him years before he was able to publish enough evidence that caused people to seriously question the geocentric theory. So, step 3, his hypothesis was that the Earth was not the center of the universe, or even the galaxy, or the solar system. So he predicted that because of the movement of Venus and Mercury, he predicted that the Earth was not the center. And what was he going to discover? Well, we know now what he discovered. So from examples here, but number 3 is a very key point. Point number 3 here. Your hypothesis must be testable. In order for it to be a valid hypothesis, it must be testable. This was one of the questions that a lot of you got wrong on the pretest. In order for a hypothesis to be valid, it has to be testable. So let me give you an example. Number 4, what color light will be best for growing tomatoes? That was in the example on the test. That's an easy one to figure that you can do. You just put up the experiment, you set up the different pots, the different colored lights, you watch them grow for a couple of weeks and you see which one grows the farthest. It's pretty easy to test. Now look at number 5 there. White chocolate tastes yucky. Some of you are going like, Mr. Plum, that's good stuff. Others of you are saying, yeah, white chocolate's not even chocolate. My wife would agree with you on that one. But is that a testable hypothesis? No, not really. Because I might like white chocolate, you might not like white chocolate. Your friend down the street might like it, but his aunt might not like it. So what you have there, number 5, white chocolate tastes yucky, that's an opinion. It's not a testable hypothesis. So not a good hypothesis. Okay, so moving along, then you set up step 4. You set up your experiment, and you have to set up an experiment or several experiments. Since we're talking about Galileo, what he was doing, now you have to, this is another key question from the pretest that some of you got wrong. The scientific method was set up to disprove a theory. In other words, he was trying to prove that the geocentric theory was wrong. He wasn't trying to prove the heliocentric theory is correct, because that hadn't even come up with. No one had even come up with that yet. He was trying to prove that the theory of the time, namely the geocentric theory, was wrong. So that's another part about the scientific method. It is designed to prove things wrong. That's what it's designed for. Okay? So obviously, if you prove that something this is wrong, then this must be true. So you see how that works? So these are 2 examples of real experiments that Galileo did. The one on the right, where you can see him, and what he's standing on there is the Leaning Tower of Pisa, the actual Leaning Tower of Pisa. It still leans. and it was leading in his time. And Aristotle had said that things move in natural motion, that there's either a natural motion or violent motion. A natural motion would be like leaves falling from a tree, or just things falling naturally. Violent motion would be if somebody shook the tree, or somebody was in the tree and they knocked the leaves off the tree and the leaf falls down. It's not natural. Someone forced the leaf to fall off the tree, so that would be a violent motion. Aristotle tried to explain the motions of the things around us with natural motion and violent motion. Galileo looked at Aristotle's thinking and thought, doesn't quite make sense. And one of the things that Aristotle said was that heavy objects will fall to the earth faster. Now that too seems to make sense. So you have something big compared to something small, you would think the heavy thing will fall faster. So you see what happens in this experiment there. And if you're with me in the classroom, you'd be able to see me do this experiment where I take a piece of paper and I drop it and it falls, and then I take another piece of paper and I have two pieces of paper and they both fall because of the air currents, but I take one of them and I crumple it up into a ball. And so then I ask the students, which one's going to hit the ground first? Everybody always says, oh, the one that's all crumpled up will hit the ground first, because logically that seems to make sense. It's more massive, or crumpled up into a ball. No, they hit the ground at the same time. And I do this with a basketball and a tennis ball, or a basketball and a ping pong ball. In the classroom, it's easy to do. And you can see they both fall, they hit the ground at the same time. Why? Because gravity pulls on everything at one constant rate. No matter how big that thing is, gravity pulls it at the same force of gravity pulling on it. So Galileo, this was one of the experiments that he was using to prove that the geocentric theory was wrong. Now, one on the left, that's a ramp. That's a replica of the actual ramp he used. And what he did was he was rolling objects, rolling balls down that track, and you can see there's the little things. There's a bell on each one of those things, and as the ball would go past, it would hit it and go ding. And so it was one of the experiments he did to test how fast things fall. Okay, so he set up multiple experiments, and there were more than this. You can look them up if you'd like. There were multiple experiments that Galileo did to try and prove that the geocentric theory was wrong. And then step 5, his analysis. After his experiments, he recorded the results, and he was proven, his theory, his hypothesis was that the Earth was not the center of the universe. So, well, let's just talk about the one experiment that he had, and two objects hit the ground at the same time. He dropped them from the Leaning Tower of Pisa there, and they hit the ground at the same time. As you can see, Aristotle was wrong. And then the astronauts wanted to prove this. Well, people argue, well, there's air resistance and all that. When the astronauts were on the moon in the 70s, they wanted to test Galileo's theory on the zero gravity or microgravity with no air friction. So they dropped a hammer and a feather at the same time, and then you would think that the hammer would hit the ground first, but in a vacuum with zero gravity and no air friction, they hit the ground at the same time, because the air friction would cause the feather to go whoosh, 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 but it didn't. So step 5, you record your results of your experiment or experiments. Final step of the scientific method is the conclusion. So you have to compare your hypothesis to the results of your experiment. What happened? Did it match your hypothesis? Yes or no? So you see here in this picture, you've got the geocentric theory on the left, and then the heliocentric theory, which helio is the Greek word for sun. So this is a more accurate theory that the sun is the center of our solar system. Okay? Now, look to your right there, and you see the scientific method in a circular form. Now, most of the time, you guys are used to thinking of the scientific method like I showed you on the second slide, where things go step 1, 2, 3, 4, 5, 6, like this. Okay? That's an inaccurate way of showing the scientific method. Scientific method is best shown like this, where you have a question, you gather information, do your research, form your hypothesis, test your hypothesis, analyze the data, interpret the data, talk about the results, and then retest. And then come up, and a lot of times what you'll end up doing is you'll end up with coming up with a new question. And so this is the more accurate way of showing the scientific method, that it is circular and that it goes on and on. And also in particular, because you'll see later as we talk more in depth about the scientific method, that in order for something to become a scientific fact or move from just a test to being true knowledge, it has to be testable by other people. So multiple people have to use your same experiment to come up with the same results. And if that happens, then it can become a scientific fact. But that's another reason why the scientific method is better shown as circular. So I hope you learned today about the scientific method, what there is, the 6 steps. Number 1, have a question. Number 2, gather information. Number 3, form your hypothesis. Number 4, test your hypothesis with an experiment. 5, analyze your data, your results from the experiment. 6, interpret that data. And then this actually, as you can see here, there's more steps because they've expanded a little bit. And then publish your results. Let people know what happened. And they've added the step here to this one of retest, which is not shown on the original slide I showed you, but it's all right. It still works. Okay? This is the scientific method, ladies and gentlemen. Hope you were paying attention because there's going to be more assignments to come.